So here is another question on electric potential. So here it is given: a uniform electric field of 300 Newton per coulomb directed along negative x-axis, and we have 3 points A, B and C located on the field. The x and y coordinates, they are expressed as in this figure. Okay, this one. Electric field represented by the red arrows along the negative x-axis, and these are the 3 points A, B and C. And we have to find the potential difference between points B and A, that is delta VBA, points C and B, delta VCB, and points C and A, delta VCA. Okay, so first let us look at the points B and A. Okay, points B and A. So if you see, they are located along the same line on the electric field. Okay, they are located along the same line along the electric field. Here, this constitutes an equipotential surface. Okay, equipotential surface means all the points lying on the equipotential surface, they are at the same potential, which means the potential difference between any 2 points on the equipotential surface, that is 0. We have discussed about equipotential surface. You can watch the video in electricity and magnetism playlist. So the first question which is asked to find the potential difference between points B and A, that is very simple and straightforward, no need of any calculation, anything. It is 0 volt because they lie on an equipotential surface, they lie along the same line in the electric field. Okay, then is CB, okay, points C and B. Here the gap between these 2 points, as they look they are located along the same line but along the electric field line, they are located along the electric field line, and the gap between points CB, that is equal to how much? 3 and 4, 4 plus 3, 7 meters. This is the separation distance. Okay, then the electric field, that is equal to 300 Newton per coulomb or volt per meter, whatever you. We know that potential difference is equal to negative line integral of electrostatic field. Okay, this, or delta V, this is dV. Okay, this is dV, not delta V, it's dV. Okay, so delta V is equal to minus E del L, the separation gap or distance. So here del L is del x CB, the separation gap between points C and B. So here delta V CB, that is equal to minus E delta x CB, the separation gap. So which is equal to minus 300 into 7, that is equal to minus 2100 volt. Okay, minus 2100 volt. Okay, this is the potential difference between points C and B, minus 2100 volt. This is BA and this is CB. Then it is asked to find the potential difference between points C and A. So here another interesting thing. Now here we see that points C and B, they lie along the same line but along the electric field line direction. But here points B and A, they are located along the same line but in the perpendicular direction. So here VB and VA, they are equal because they lie on the equipotential surface. So as potential at points B and A are equal, so delta VCB is equal to delta VCA, because potential of points A and B, they are the same. So delta VCB is the same as delta VCA, which is equal to minus 2100 volt. Okay, this is the thing. So here, why points A and B, they are the same potential? Because we know E is equal to minus dV by dx. So here, as they are along the same potential, dx becomes 0. There is no change of electric field. Okay, there is no change of electric field. So they are along the same line in the perpendicular direction, so they are at the same potential. There is no change in potential between these 2 points. But here there is some value of separation gap between these 2 points. So as there is a separation gap, so this dx, the product of these 2, that contributes to a change in potential difference. But when delta L is equal to 0, here when delta L or delta X, whatever, the separation gap is equal to 0, in that case, any value of electric field multiplied with 0, it will be 0, which is equal to the change in potential difference, the change in potential. So when they are along the same line in this direction, there is no change in potential difference. They are at the same potential. Okay. So here is another question on electric potential. It is given that a small particle carrying a negative charge of 1.6 into 10 to the power minus 19 coulomb is suspended in equilibrium between the horizontal metal plates 5 centimeter apart, having a potential difference of 3000 volt across them. Okay, find the mass of the particle. Okay, this is given. So here we have 2 metal plates, where let's say this is the positively charged metal plate and this is the negatively charged metal plate. So the electric field, it will be in this direction. Okay, here we have a charge, negative charge 1.6 into 10 to the power minus 19 coulomb, that is the charge on the particle. Mass is, we have to calculate, we have to find. So here the separation distance, okay, let's say the separation distance between these 2 plates, that is equal to 5 centimeter, okay, which is equal to 5 into 10 to the power minus 2 meter, and the potential difference between them, dV, that is equal to 3000 volt. So we know electric field, that is equal to negative potential gradient. So here we are concerned only with the magnitude of the electric field, so that will be equal to dV by dr. Actually it is negative potential gradient, but considering only the magnitude, that is equal to dV by dr, that is equal to 3000 by 5 into 10 to the power minus 2 meter. So it is coming 6 into 10 to the power 4 volt per meter. Yes, 6 into 10 to the power 4. Now this is the electric field magnitude. Now we know that whenever such a situation is there, it is said that it is in equilibrium. Equilibrium means it is not moving either upwards or downwards. It means two forces are acting on it here because of its mass and acceleration due to gravity. A downward gravity force mg, and as it is a negative charge, it will experience a force of repulsion from the negatively charged plate at the bottom. So an upward repulsive electrostatic force of repulsion. So since it is in equilibrium, the electrostatic force, that is equal to the force of gravity. The electrostatic force we know that is equal to QE. Okay, QE, and this is equal to mg. So QE is equal to mg at equilibrium. Okay, at equilibrium. That implies the mass is equal to QE by mg. Sorry, QE by g. Sorry, QE by g. This one will not be there. QE by g only. QE by g, which is equal to 1.6 into 10 to the power minus 19 coulomb, considering only the magnitude. E is equal to 6 into 10 to the power 4 volt per meter by 9.8. It is coming around 9.8 into 10 to the power minus 16 kgs. Okay, so this is the mass of the particle, 9.8 into 10 to the power minus 16 kg. Okay, so this is the thing. Okay.